we have discussed just generating and AM and FM signals and have also looked at their spectra, right? So, but the question, as since in the first lecture I promised that this course has direct practical implications. So this is a good time to look at those practical implications. The first practical implication that we'll talk about will come here later, but we'll talk about the first practical implication that is not in the notes that I pasted here. That is frequency division multiplexing. So want to transmit signal. Who else wants to transmit an AM signal? Raise your hand. Who other than me wants to transmit an AM signal? Raise your hands. Come on. No one. Yeah. Gandhi wants to transmit AM signals. Yash wants to transmit an AM signal. Good. Pavan. Sorry, Pavan wants to transmit an AM signal, not Yash. Okay. Yash, you don't want to transmit an AM signal?
FM.
We want to transmit FM. Okay, cool. So Gandhi, not MK Gandhi, wants to transmit AM. Pavan wants to transmit. So what I will do is, so let the bandwidth of the signal be WR, WG, WP. And what I can do is I can design that. Oh, sorry. Yeah. Let of say, let's call the signal MRT. MRT be FC. Then if the carrier of MGT is F plus delta, sorry, FC plus WR, because it takes double the bandwidth, plus WG delta MPT is FC plus plus 2WG plus 2 delta, then I can represent the frequency spectrum as 0. So let this be my frequency FR, bandwidth WR plus FC, C plus WR. You give a guard interval. So delta, let me call the guard band. Here is Gandhi's signal, and here is Pavan's signal. So let me call this FG, and let me call this FP. Fine. And using a suitable demodulator and bandpass filters, I can separate these three out at the receiver, right? You guys agree with this approach? At least Pavan and Gandhi. You can separate out your signals from mine using this approach. And I provide a guard interval of delta so that to let the cutoffs of the two filters cool off. Pavan, Gandhi, okay?
Yes, sir.
Great. So I can actually, so can transmit 3 channels and receive them. This is called frequency division multiplexing. FDM. And this has been used in all, this is used in all your radios. All radios means broadcast radio. And this has been used in case of pre set top box television. You guys know pre set top box television, right? You're not that young. And you, yes, so this. So now let us look at a practical receiver for AM. This structure here is called the super heterodyne receiver. Fine. This is called the super heterodyne receiver for AM. And how does this work? Or I'll tell you how does this work. You have heard about tuned amplifiers in your analog circuits course? Chandra, have you heard about tuned amplifiers? Yash, tuned amplifiers in the,
I don't remember, sir. There
oh, don't
might be.
remember. Okay. Pavan, Gandhi, you had something like that? Tuned amplifiers in the analog circuits course.
I don't remember, sir.
Okay, cool. Hey, if I end up teaching you digital communication in the next semester, don't say that you don't remember things from this course. Anyway, so a tuned amplifier. So basically, what we need is that the circuit operate at uh, operate close to the carrier frequency of the system, and for that since we want bandpass filters and all, so bandpass filter to filter out the desired component of the signal. So we need a bandpass filter to filter this out or filter this out or filter this out. So because of that, we need a bandpass filter and a bandpass filter with adjustable L and C components, right? So now adjusting the L and C components at such high frequencies can be an issue. So what Armstrong, we had Armstrong's picture in the first lecture. So what Armstrong proposed, so not Edwin H. Armstrong, not Neil Armstrong. That why? What this guy proposed back in 1910 was that instead of having a variable, so basically we would need a variable inductance and a variable capacitance for the tuned amplifier, which is unreliable. So you have not worked with variable inductances, right? Physically. First year course, did you work with variable inductance? First year lab?
No, sir.
No, sir.
Okay. No, okay. So you don't have an idea how unreliable that stuff is. So variable resistance is one of the easiest things to implement. Variable capacitance and variable inductances are ridiculously hard to implement. Most of the time the equipment in our lab most didn't for variable inductance and variable capacitance didn't work, but we have developed relatively reliable fixed capacitances and inductances. So what we have is that we shift everything to, we use a tuner so that or a variable local oscillator. Local variable local oscillator is easy to generate. You know, voltage controlled oscillator or such stuff. So those things are easy to generate. So we have a variable local oscillator that uses a variable frequency so that all the frequencies, all the incoming frequencies are translated, and the frequency you desire or the frequency you want to work with is translated to something called the intermediate frequency or the, and everything is taken care of, or all the remaining circuits, the remaining and remaining circuits are designed fine. So this was the idea of Edwin Armstrong, and this was his patent. And one of the reasons that okay, let's not talk about that. So yeah, one of the patents that led to Armstrong-Chernoff wars. You can those are not like the Star Wars Clone Wars or not like the Star Wars movies, but yeah, interesting stuff from communication history. So interested people can look that up. And so this is this local oscillator generates frequency Fc plus I. This is the intermediate frequency. And we know that when this local oscillator multiplies with the incoming signal, we'll have a signal at the intermediate frequency and we'll be happy. But at the same time, what happens is that so therefore Fi equals Fc plus, or rather minus Fc, right? But since both plus and minus or multiplying with cos 2 pi f LOT both FLO minus FC and FC. These two components will be generated. Now, since both of these components will be generated, this is called the image component. This we don't want, but this comes in because of mathematics. So this is called the image frequency and is an issue in case of super heterodyne receivers. But we get rid of this via uh, an image rejection filter before so so that we do not have interfering signals. Fine. So you see that Fi so will be this, or Fc equals, sorry, I'll re-say this because I think I haven't made myself clear. So if the image or the IF is Fi, then Fc equals FLO minus Fi. F, yeah, will be translated to Fi after mixing with the, but the same time Fc prime equals FLO plus Fi will also be translated to Fi. This is called the image frequency, and once this is translated to Fi, we cannot get rid of this. So the solution is to filter out the image frequency before fine. So this is how the super heterodyne receiver works. Any problems with this? Okay. Since we have described the super heterodyne receiver for AM, we'll also talk about Yash. You want to run FM, right?
Sir, I had a doubt.
Yeah,
How do we generally choose FI?
FI. So I'll just list out actually, because these days these things are no more chosen. But FI is generally chosen so that it is large enough so to have a respectable amount of gap between the image frequency and the true frequency one, and small enough to allow simple processing, because for large frequencies it's hard to design all these circuits, band pass filters and all. It's very hard to design or band pass filters, resonant circuits at high frequencies. It's very hard to design them. That's why we most of your cell phones still operate at 2 gigahertz. That after so many years of research in electronics and communication. So generally we want this Fi to be small, because we have to have good circuits, and it has to be large so that the true carrier frequency and the image frequency are far enough. So something in between, or the Goldilocks frequency lies somewhere in between. So for for classical AM radio, I'll just give out so the numbers. So see, commercial AM radio broadcasting utilizes the frequency band this 535 to 1605 kilohertz for voice and music. The frequency range with a 10 kilohertz spacing. So two bands are 10 kilohertz spaced. So the music quality shouldn't be that good. Actually, the music quality would be quite bad, because 10 kilohertz is not a bandwidth where you can transmit quite a lot good quality music. So radio stations employ conventional FM for transmission. The baseband message signal is limited to a bandwidth of 5 kilohertz. So 5 kilohertz is barely good enough for voice. And so yeah, practically you choose this IF to be 455 kilohertz. Answers your question, Yash?
Yes, sir.
Great. And similarly, I'll paste a page for actually this you can read yourself, but I'll simply paste a page for FM since we are talking about it. And this you can read like a story. I need not tell of all of this, but yeah, since we have started this, let me finish at least this section, and then I'll talk about color, and then we'll move on to the next part. So yeah, so what is the range for FM? You guys tell me. You need not copy paste it from the book. FM. Come on.
Around 90 megahertz.
90 to
80,
130.
88 to 108 megahertz. Look at the your phone's FM radio or car radio today after the class. Fine. 108 मेगाहर्ट्ज पर विविध भारती चलता ही चलता है. if nothing else works. But FM is relatively short range, and actually, so FM again has this. So FM also uses super heterodyne receiver, and supports stereo sound. Stereo sound means that yeah, so FM signals have a bandwidth of 200 kilohertz. Oops. Yeah. Bandwidth stereo supported. Stereo, you understand? Stereoscopic sound. What is it?
No, sir.
You
Left and right ear.
you you use stereo speakers, right? Your laptop has speakers and proudly claims that those are stereo speakers.
Separate channel for left and right
Yeah,
ear.
yeah, separate stereo. See what stereoscopic sound means separate. Who said this otherwise? Separate channel for left and right. Gandhi, you said that or someone else said that?
Sir, me.
Yes.
Oh, yes. Okay, yes. Okay, separate channels for left and right. So, uh, Navya, say suppose you are blindfolded and put in a room. Suppose, and you are told that you can get out of the room by following the speaker who is at the door, and he'll just speak. So what you will do is you will try to figure out the direction from the
Yeah,
uh,
get the source.
yeah, direction of the source, and then move towards that, right?
Yes, sir.
And get to the door as fast as possible. Now, uh, if I close one of your ears, you won't be able to do this because our
Oh,
sense of direction comes from the fact that there are two inputs in our head, or we have 2 ears. Because we have 2 ears, we use that, okay, this is the left ear, this is the right ear, and this is the our head knows that this is the approximate circumference of my head, or this is the approximate diameter of my head, so that a signal from this far away would impact the left ear like this and right ear like this. And because of this difference in sound, we are able to perceive the direction. Okay, this is a, you don't need to solve all those equations every time you figure out the direction of a source, but that's what the neural network in your head is doing. Every time you hear something different from the 2 ears. So that kind of a sound is called stereoscopic, but not all FM radios are stereo enabled. So what they do is over one channel. So the 200 kilohertz FM channel is divided into two sub channels of 100 kilohertz each. And over one channel, they transmit the sum of the two signals, the left and the right channel. And over one channel, they transmit the difference of the two signals. So it, the left channel is called the L channel and the right channel is called the R channel, predictably. So what they do is, if a radio is stereo capable, then it decodes both the channels, or it demodulates both the L channel and the R channel and combines them, adds and subtracts them to get a get separate outputs for the left speaker and the right speaker. If the stereo is, if the receiver is not stereo capable. It simply demodulates the sum of the two systems and gives the output to you. Fine. So stereoscopic makes sense.
Yes, sir.
Yeah. So since we are talking about stereoscopic sound, let's talk about stereoscopic vision. So uh, has anyone watched? Okay, all those who watched Avengers Endgame, raise your hands. So I also now I also remember that Avengers Endgame came out while you were having those your all your exams and all, right? JEE and all. So JEE is May. Avengers came out in April. Yes, 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 yeah, I get that. I get that. So okay. Anyway, the point is that you go to a movie hall and they 3D. 3D is the expensive thing, and 3D is the only thing that your home television or your laptop does not have to offer. Otherwise, 2D you can watch anywhere. So, what's so special about or and you would have noticed that they give you some glasses when you go for 3D viewing, right? Now, when you go for a 3D movie, they give you glasses, right? So if you try to watch the movie without those glasses, you see the same movie but blurred. But if you want to watch the movie with the glasses, you'll see that in addition to the X and Y, so on a screen, the screen is a two-dimensional surface. But somehow with those glasses, you are able to see X, Y, and Z coordinates on the screen, right? So any guesses on how this works?
It has polarization filters.
Yeah, Bala, it has polarization factor. Now explain this to me.
One is,
Polarization you will study in your electromagnetics course later.
yeah, that means we can receive the perception of the depth by having two eyes.
Yes.
So to give that same depth, we need two images.
Yes.
There will be
And
two projectors projecting the left and right image on the same screen,
yes.
and
But the light
the angle
from
between them is 90. Polarization angle.
the angle of polarization. Yes. The angle of polarization you will study better in your electromagnetics course. But the fun thing is that the one of those the 3D goggles or whatever you call that at your in your city. So those 3D glasses. The fun thing is that one of the glasses is horizontally polarized and the other one is vertically polarized. So one glass allows image from one projector and the other glass allows image from another projector. So you actually see two images, one on each eye. And since you see one image on each eye, and again, this is your head is a complex neural network. What it does is that like the screen, the retina of our eye is also a two-dimensional surface. We can only project a two-dimensional image onto it. So someone who unfortunately has a single eye since birth can only see in 2D. They cannot see in 3 dimensions. They can only perceive X and Y coordinates of what is out there, which is unfortunate. Anyway, so our brain learns to look at a three-dimensional image by estimating the depth from the two different images that are impinging upon the eye. Makes sense? Again, neural networks, or it's mostly machine learning. No, the involved mathematics is ridiculously complex. Make sense?
Yes, sir.
Great. So this is called stereoscopic vision. And if you go back to your class 9 biology books, class 9, I don't know, they would have changed that. We had this in class 9th and class 8th that humans are the only species, maybe class 8th or class 9th or something like that. That humans are the only species to possess stereoscopic vision. Yeah, obviously class 9th biology is famous for other reasons as well, but let's not discuss those. So yeah. So we have stereoscopic sound, we have stereoscopic vision. Now let's talk about the other most famous broadcast communication system that has had me beaten up many times in my childhood. Television. So I'll just run through the modulation standards. So television is basically 5 megahertz signal with 4 megahertz. Excuse me. Yeah, 4.5 megahertz. 4.5 megahertz image, 4 megahertz bandwidth, 500 kilohertz vestige for so you remember vestigial sideband modulation, right? This is where it is practically used, and 500 kilohertz FM audio. So high quality FM audio plus uh,
So 5 megahertz for what?
television band. The television signal bandwidth, Ashwin, is 5 megahertz, out of which 4.5 megahertz is for the image. And actually, the image actually occupies 4 megahertz, but we give a 500 kilohertz additional vestigial sideband, and there is a 500 kilohertz FM audio signal associated with that. This is black and white television. This is the classical black and white television that you had even before I was born, let alone you guys were born. This was the system that was followed before any of us was born, but still it's interesting. So actually what I would recommend is that this section 3.4 radio and television broadcasting, you just go through this once. This is interesting reading, but this is not something that can be yeah, and this is not something that can be taught in the class, or not something that so this is mostly story stuff. You need to, there's no need to remember this, but still all of this is interesting to know. So I'll just touch upon this and continue. So also let us talk about, so there are two things. Let's first talk about the one related to communication. This is a good time to introduce 1G. So 1G systems were two-way FM radios using separate frequencies for transmission and reception. Ideally 1G. This was 1G. So 1G was FM. Just list out the other generations for completeness. Oops. $1990,000. Actually, it shouldn't be 2000 because people are still using 2G. And it started 2G came in 1990. So 1G was 1980 to 1990 because 1G isn't backward compatible, or 2G systems aren't backward compatible with 1G. 2G is 1990 onwards, and again MSK based 3G 2000 CDMA based 4G OFDM 5G also OFDM MIMO, OFDM large MIMO, OFDM multi-user MIMO. So this we'll cover in this course. This will be covered in an elective on wireless communications. Fine. So we limit ourselves to, in this course, we'll build the background for the next. So we'll build the background for the other generations of this course. Fine. Yeah. Okay. Yes. So we have like 15 minutes. So let me introduce what we'll do in the rest of the course. So till now, we have considered modulation using cos 2 pi fct or 2 pi fmt signals where the information signal is you know what are deterministic and random signals? Pala?
Sir,
Yeah, you know what are deterministic signals and random signals?
I think from name I can guess, but I'm not
Yeah,
sure.
guess.
Random signal means we get something like noise.
No.
I think I didn't think
Okay,
there
so
is.
let me.
Maybe like that, it gives a random value where it is like a deterministic signal, like there is some sequence or some.
Yeah, okay, now yeah. So let me. So a deterministic signal deterministic signal is a one that can be fully characterized by a mathematical function at any point of time. Fine. A random signal is a signal that is not deterministic. Fine.
Sir, we can write anything in as a function of as a function, right?
You can uh, at any function at any point as a function of time, and hence its future values can be exactly did. Fine. Ashwin makes the definition slightly more clear. Cos 2 pi fct. Deterministic. E to the power minus
Yeah.
t. Gate function deterministic. E to the power minus t something deterministic. We mostly deal with, till now we have dealt with these functions. We are exclusively dealt with these functions till now, right? But one problem is that if we want to transmit a deterministic signals, then what is the fun of it? Because if I want to transmit a deterministic signal as a function of time, I can instead simply send the functional form. Why waste all this bandwidth? You agree with me? Or so you guys, the lockdown started in your first year, right? While you guys were in your first year.
Yes, sir.
Yeah. So how many of you started watching Game of Thrones when you came here, or when you were here, or Sherlock for that matter, or anything with suspense? Anyone read Sherlock Holmes
I
or
read
any
Game of
mystery?
Thrones.
You have read Game of Thrones. Wow. So Gandhi, what's the, okay, I tried reading that back in 2012. It was horribly slow. I don't know. Sorry. Sorry, I don't want to hurt your feelings or something.
No, sir. It's
Yeah.
true.
Yeah. Lord of the Rings, bearable. Lord of the Rings I've read more than once. Harry Potter I've read 10 times. That is a different thing. But yeah. So anyway, so the thing is that you won't read that. Had it been, would you read that if that was a deterministic signal?
No, sir. I mean, if it is pretty predictable, we lose interest.
If it is pretty predictable, you lose interest. You uh, keep your interest because you are thinking that Ned Stark is the main character, and halfway into the first book, his head is chopped off. No, sorry, in the books, he's stoned to death, right?
No, his head is chopped.
His head is chopped. Okay. Okay. Yeah. So halfway into the book, his head is chopped off, and so that is randomness.
So you just gave spoilers to all the people here.
I'm sorry, Shirish. But I believe that spoilers for something that has been out for more than 2 years now.
Yes, sir.
Most
Yeah,
people would have seen
yeah,
or read it.
yeah, yeah. So anyway, uh, I didn't give endgame spoilers.
Who would not have seen that, sir?
You haven't seen endgame? Okay, cool. No
I mean,
problem. No
what?
problem. No problem. No problem. Yeah. So yes. So the point is that these things, you are interested in things, or things contain information only when they are random. You agree with that? Or information is a function of randomness, more or less. We obviously maybe towards the later half of this course, or in the second half of this course, we will define what is information. We'll study its dependence on randomness. But right now, you would agree that randomness is interesting, or randomness contains information. You agree on that? Shirish, Gandhi, Bala, Ashwin, Navya, Yash, Pavan.
Yes, sir.
Yeah, so the interesting thing or the informative thing is randomness. Actually, me telling you that randomness is interesting would also have been random. That's why suddenly people have started interacting, which is a good thing. Yeah, anyway, so it's randomness which is interesting. So the next thing that we will do here, or the next thing we'll do here, is we will formally characterize randomness and see how it relates to information. We'll also see the effects of this randomness as noise, as many of you perceived a non-deterministic signal to be. So we'll also look at how randomness behaves as noise, and how it affects the performance of AM and FM systems. But we'll also see the good part of randomness, and we'll develop or we'll redevelop the theory of probability that you have studied in the last semester. Also, before we let off for today, we'll just I'll just write down two words. Random. So right now, these are synonyms for you. Or most people don't even use the word arbitrary, they use random. Right? So we will by the time we end this course, the word random will have a proper meaning, or a random will be random is structured randomness. What is arbitrary is what we use for random. So we'll talk about structured and unstructured randomness as well. So we stop here. This, I believe, was a good, what do you call it? Good break or good pit stop before we moved from one set of the lectures to another. So any questions? Great. So we'll start off with randomness tomorrow. Okay. Bye all of you. Have a nice day.
Have a nice day, sir.
Bye.